Hello friends, so today we are going to solve few questions, and these questions were asked in the year 1995, 1994, 1993 and 1992. So in the first one, which was asked in the year 1995, and it states that a battery is connected between 2 points A and B on the circumference of a uniform conducting ring of radius r and resistance capital R. One of the arcs AB of the ring subtends an angle theta at the center. The value of the magnetic induction at the center due to current in the ring is. In this case, we are given a ring, and this ring is connected to a battery. And between 2 points A and B, and this point subtend angle theta at the center. So suppose the battery is supplying a current I. So this current I can be divided into two parts, current I1 and to the other part current I2, and this other angle can be written as 2 pi minus theta. So now we have two currents and two separate arcs. So let us call one arc as, let us mark this point as C and this point as D. So we have two arcs ADB and arc ACB, and we have a supply that is our E. So therefore we can write first of all how the current will be distributed, because resistance R is given for the total ring. So we have to find out the resistance of the arc AB and the resistance of arc ADB. So we have current distribution, and we are given total resistance of ring this is given as a capital R, and because of this battery, the ring is divided into and we had this ring like this. So because of this 2 points A and B, the ring is divided into two arcs. Okay. So we can say that our arc ACB, its resistance is suppose given as R1. That R1 we can write our R theta divided by 2 pi, and we have second arc, and that is our ADB. Its resistance is suppose R2, and that value of R, its angle is 2 pi minus theta divided by 2 pi, and the respective currents is our I1 and I2. Okay, so current ACB can say arc ACB, the current is our I1, so which will be equal to our, let me write it, V, much more convenient, V upon R1, and we substitute value of our R1, we get this as our I1 is equal to 2 pi V upon R theta. Then we have arc ADB, and current is given as I2, which will be equal to V upon R2. We substitute value of R2, we get this as 2 pi V upon R, and this is about 2 pi minus theta. Now we can find out the magnetic field due to each arc at the center. Magnetic field due to each arc at the center of the ring. Center of ring. And we say that the general formula, we can write that this, if it is equal to B, then this will be equal to mu naught I upon 4 pi R and multiply by phi. Okay, where phi is the angle subtended at the center. Now in this case, the angle is our theta and 2 pi minus theta. So here in this case, we can say that R is the radius of circular arc. R is the radius of ring, and phi is the angle subtended at the center. Angle subtended at center. So we can divide this into two arcs. So first of all is our ACB, and here our phi is equal to theta, and the field is our B1, so this comes as mu naught I1 upon 4 pi R multiplied by theta. And now we have ADB, here phi is our 2 pi minus theta, so the magnetic field is our B2, which will be equal to mu naught I2 divided by 4 pi R, and this comes as 2 pi minus theta. Now we have to find out the direction. Direction of fields. Now the current flow I1 and I2 are in opposite. One is clock, other one is anti-clock. You can say currents I1 and I2 flow in opposite direction. It means the magnetic field at the center will oppose each other. So you can say magnetic field at the center oppose each other. Oppose each other. Therefore, net magnetic field B net will be equal to our B1 minus B2, and which you can write mu naught upon 4 pi r, and this comes our I1 theta minus I2, and this is 2 pi minus theta. And we substitute value of our equation for our I1 as well as I2. So this gives us mu naught upon 4 pi r. I1 is our 2 pi v upon r theta multiplied by theta minus, and this is 2 pi v upon r into 2 pi minus theta multiplied by 2 pi minus theta. And this theta 2 pi minus theta cancels out, so we get this as mu naught upon 4 pi r. Here we have 2 pi v upon r minus 2 pi v upon r, and these two also cancels out. Therefore we get that the net magnetic field at the center will be equal to 0. And this particular net equation we can also understand is independent of theta. Okay. So we can say it will be 0 for all values of theta. It will be 0 for all values of theta. Therefore, the option D is the correct option. Option D is correct. Now we come to the next question, and here it says that it was asked in the year 1994, and it says that H positive, 1 positive, helium 1 positive and oxygen 2 positive, all having same kinetic energy, pass through a region in which there is a uniform magnetic field perpendicular to their velocity. The masses of H positive, helium positive and oxygen 2 positive are 1 AMU, 4 AMU and 16 AMU respectively. Then we do check which of the options is correct or are correct. Okay. So it is given that we have a uniform magnetic field and which is perpendicular to their velocities. So because of this, the particle, the respective, you can say, masses will be undergo a uniform circular motion. So you can say when a charged particle enters a magnetic field perpendicular to its velocity, it undergoes uniform circular motion. Uniform circular motion. Therefore, we can write that the radius R will be equal to mv divided by q multiplied by b. Okay. And we are given that all particles have same kinetic energy. All particles have same kinetic energy. Let us suppose that it represented as K. So we can say our k is equal to half mv square. So here we can find out our velocity. Velocity will be equal to 2k divided by m and its square root. So we substitute the velocity in the radius equation. Let us call this as 1 and this as 2. So using equation 1 and 2, using equation 1 and 2, we get our radius r is equal to m upon qb multiplied by 2k divided by m, which can be further written as square root of 2km divided by q multiplied by b. So from here it is quite obvious that our radius is proportional to square root of mass divided by charge. So we can just prepare a table and check for all. So first is our particle, and then we have mass small m, we have a charge q, and we have the equation that radius is directly proportional to square root of m and inversely proportional to q. So first particle is our H positive and mass is 1 AMU. Yeah, for the sake of simplicity, let us call this as A. Charge is our plus E. So here we get that the radius will be equal to square root of A and divided by E. Second one is our He positive, so which have 4, okay, it will be 1. 4 AU, charge is plus 1, and so we get this as 4 AU divided by charge and its square root. So this comes as 2 AU and its square root. The last one is our O2 positive, which is given as 16 AU. Charge here it is about 2E. So we can write this as square root of 16 AU divided by E, and this will be coming as 4 AU divided by E. Sorry, 2E, my mistake. And this will be our 2 and 2 goes away. So we get this as 2 AU divided by E. So from here we can clearly see that the value of the radius for He1 positive and oxygen 2 positive is same. And if you make a comparison, you can understand that the radius of the hydrogen H positive is the smallest one. You can say that H positive has the smallest radius. So because of this, it will be having most deflection. And our He positive and O2 positive, they have equal radii, and they have equal radii, so which basically means equal deflection. They will be having equal deflection. So the option, if we check, is our option number A is the correct one, and option number C is also correct one. So option A and C are correct. Option A and C are correct. Next question. It was asked in the year 1992, and it says that a straight segment OC of length L of a circuit carrying a current I is placed along x-axis. Two infinitely long straight wires A and B, each extending from Z minus negative to minus infinity to plus infinity, are fixed at y is equal to minus a and y is equal to plus a respectively, as shown in figure. If the wires A and B each carry a current I into the plane of the paper, obtain the expression for the force acting on the segment OC. What will be the force on OC if the current in the wire B is reversed? So in this we have two parts rather. First says that each carry current which is into the plane of the paper. It means direction of the current is same. So this figure is drawn according to this first part. The direction of the current at both A and B are same, that is into the plane of the paper, and they both are at a distance of A. So this is our at a distance of A, negative y, and this is also at a distance of A, that is our positive y. And this is line segment which is carrying a current I towards positive x-axis. So we have to find out the force acting on this particular line segment OC. And in the second part it says that the current in the wire B is reversed. So because of the current that is flowing through A and B, we can say that, let me mark a point P on this OC. So let us suppose this is a point P, and the magnetic field at this point P, because of the current flowing through the wires A and B, will be perpendicular to AP and BP respectively. Okay, so let me draw the figure. So in this case, the direction of the magnetic field due to B at this point P will be perpendicular, and its direction will be something like this. Because of A at point P, the magnetic field will be along this direction, perpendicular, and that let's call that BA. And because of the current flowing through B, the magnetic field at this point P will be perpendicular, and it will be having this direction. Let us suppose that is our BB. And the angle with which we call this angle is theta. Our other one will be also theta because they are symmetrical about y-axis. So we can say that the magnetic field at P due to current in the wires A and B will be in the direction in the direction perpendicular to AP and BP. And for this we can say that our BA will be equal to mu naught upon 2 pi and the current flowing through it and the distance of AP. And we can just, you can say, divide this. Let me draw it here. So this is our point P. We have a magnetic field BA, and this BA can be divided into two components. This will be one part BAX and the other part will be our BAY. And we have second one, that is our BP, which can be divided into two components. One will be our BPX, and this is our B. So this will be our magnetic field of B in X direction, and for Y direction it will be same. So this will be a magnetic of B in Y direction, and this will be our angle theta. Okay. So from this figure we can clearly understand that the magnitude of our BAX will be equal to our BBX. So therefore the net magnetic field in X direction will be equal to 0. So only magnetic field that will be present will be in Y direction. So you can say that components of magnetic field because of wire A, we are going to have two components. One will be our BAX, and obviously that will be our BA sine of theta. Second component will be our BAY, which will be equal to BA cos of theta. And similarly we can write component of, due to wire component of BB, so it will be BBX, and that will be our BB sine of theta, and we are going to have BBY, which will equal BB cos of theta. So the component along x-axis are equal and opposite. Therefore magnetic field in X direction net will be equal to 0, whereas the magnetic field in Y direction net, let us call for the simplicity it as B, will be equal to, and here the magnitude of B will be equal to, this will be BA cos of theta plus BB cos of theta, but the magnitude of BA and BB is same. So therefore we can write that the magnetic field will be equal to twice b cos of theta, and we can substitute value of this b, and let me make a distinction, otherwise it will create confusion. Let us call this as b net. So we can say that our b net will be equal to twice multiply by, we have this as mu naught upon 2 pi, and we have current I upon AP, and for angle theta we can say here cos of theta will be equal to x upon AP, and this is our cos of theta, and we can say that our magnetic field net will be equal to, here 2 cancel with 2, so we are left with mu naught upon pi I upon AP, and cos of theta will be our x upon AP, and this can be written as mu naught I upon pi, and here comes as x upon AP square, and AP we can write in the form of A and x. We can say that our B net will be equal to mu naught upon pi, and this comes as x upon our AP square rather is our A square plus x square. So we substitute, we get this as A square plus x square. So let us consider a small element along this line. Okay, so we consider a small element, and the small element is of dx. So we can find out the force on the small element dx. The force on small element dx. So we get our df is equal to our I, and we have just found out our magnetic field, that is our mu naught I upon pi, and we have x upon A square plus x square, and multiply by dx, and this force will be in our negative z direction. Negative z direction. So we can find out total force along the wire. Total force on the wire, and the length of the wire is given as capital L. Therefore we can write that our F will be equal to integration from x to 0 to x to L df, and this comes as mu naught I square divided by pi integration 0 to L. Here we have x dx divided by x square plus A square, and this will be nothing but, because it's derivative we can just create it, we can just multiply 2 and 2, divide and multiply by 2, so automatically the derivative of denominator is in the numerator. So we get our force F will be equal to mu naught I square upon 2 pi natural log of L square plus A square divided by A square. K unit vector and with minus sign. So this was the first part, and in the second part it says that the direction of the current in the wire B is reversed. So now we can draw a rough approximate diagram. So we have this as point B. Now direction is reversed and it is along y-axis. We still have the wire along x-axis, so this is our C. Current is flowing in this direction, that is our I, and we have other point that is A, which is having current C in the same direction, and this is our Z. Now we can easily find out that because of the current that is flowing in A, the magnetic field is suppose our BA divided into two components. This is our BA Y and this will be our BA X. And now because of the direction of current that is reversed, the magnetic field because of B will be in this direction perpendicular, which is our BB. And so we can also divide it to two components. This will be our BA. I think, let me 1 second. Yeah. So this will be our BAY, and we are going to have this BA, our X. And the direction of, you can say, B is reversed. So you can clearly understand that the net force will be equal to 0. So in part B, we have when the direction of current in B is reversed. B is reversed. The net magnetic field is along the current. Therefore, along the current means here our BAY will be equal to BBY. So because of this, net force along Y will be equal to 0, whereas our net magnetic field along X direction will be our BAX plus BBX, and the net force along our X direction will be on X-axis. So its direction will be along not the direction of net magnetic field. The direction will be along the current. Therefore, net force will be equal to 0. So these were second question. Anything else? Yeah. So let us move to next question. And here it is asked that an electron gun G emits electron of energy 2 keV traveling in the positive x direction. The electrons are required to hit a spot S where GS is equal to 0.1 meter, and the line GS makes an angle 60 with the x-axis as shown in the figure. A uniform magnetic field B parallel to GS exists in the region outside the electron gun. Find the minimum value of B needed to make the electron hit S. In this case, first of all, the electron is moving at a certain angle, that is with respect to the magnetic field. So therefore, the electron will follow a helical path. And it was asked in the year 1993. You can say that our magnetic field is also parallel to GS. And the electron is traveling in positive x. Electron is traveling in this direction, positive x-axis, and magnetic field is at an angle of this velocity. You can say that electron is moving in a magnetic field at an angle. Therefore, electron follows a helical path. Which basically means a spiral. Now it is going to hit the target S, and only for certain value of pitch of the helix and the length GS. You can say electron will hit the target along the direction of magnetic field, along the direction of magnetic field, depending upon pitch of the helix and length GS. And we have to find out the minimum value. Okay. So we are going to start with the energy of the electron, because energy is given. From there we can find out the velocity, and then we can use that to find out the pitch and other things. So first of all, we are going to find out the velocity of the electron. Velocity of electron, and we are given its kinetic energy. We can say kinetic energy is equal to half mv square, or we can say our velocity v will be equal to 2k divided by m and its square root. We substitute values, we get 2 into 3.2 into 10 to the power minus 16, and mass is 9.1 into 10 to the power minus 31 and its square root. So this gives approximately as 2.65 to 10 to the power 7 meter per second. Now we study the motion of the helix. Motion of electron is helix. Therefore, we can find out its pitch with already the formula. Pitch of the helix, which basically means distance moved along B in one full turn. Distance moved along B in one full turn. In one full turn. And P is equal to 2 pi m divided by q b and cos of theta, and v cos of theta. V cos of theta, and this v cos of theta is the component which is along the magnetic field. V cos theta is component of velocity, along magnetic field. And we require that to hit the spot S, it is given that the distance is 0.1 meter along the direction. Okay. You can say that hitting point S, lies at a distance GS, which is our 0.1 meter. And for the condition, is that the distance GS is equal to n multiplied by p, and with substitute value of p, that is our pitch, is our 2 pi m divided by q b, and this we have v cos of theta. Therefore, magnetic field will be equal to n 2 pi mv cos of theta divided by q multiplied by gs. And for minimum value of b, the value of n should be equal to 1. For b is equal to b minimum, n should be equal to 1. Therefore, B minimum will be equal to 2 pi mv cos of theta q multiplied by gs, and we substitute the values. This is 2 pi into 9.1 10 to the power minus 31 multiplied by 2.65 into 10 to the power 7 divided by cos of 60. Cos of 60 is a 1 by 2. So multiply by 1 by 2. Charge is 1.6 into 10 to the power minus 19. GS is given as 0.1. So this B minimum will be approximately equal to 4.73 into 10 to the power minus 3 Tesla. So this is the minimum value of the magnetic field. Now we come to the next question. It says that it was asked in 1994. It says that a long horizontal wire AB, which is free to move in a vertical plane, carries a steady current of 20 ampere, is in equilibrium at a height of 0.01 meter above another parallel long wire CD, which is fixed in the horizontal plane and carries a steady current of 30 ampere as shown in figure. Show that when AB is slightly depressed, it executes a simple harmonic motion. Find the period of oscillations. So we can just, you can say, carry out the entire discussion in two parts. So part 1, the figure is already given to us. It says that we have wire AB and wire CD, and the distance between the two, it is given as 0.01 meter, and AB is equilibrium with CD. The direction of current in both is same. And in second part, if we assume that we push the wire, let us suppose this is our AB, and this wire AB is pushed slightly in the downward direction, coming to A prime, B prime, and this distance is our X, and CD is our fixed. And in the first case, AB is in equilibrium, so the force of the magnetic field because of CD, let us suppose we call this as F magnetic, and downward direction we are going to have our mg, and they both should be equal. So we can say that this is our part 2. So in part 1, we have gravitational force downward, magnetic force upward. Gravitational force, which is our downward direction, will be equal to magnetic force which is in upward direction. And so gravitational force is our Fg, which we can write our mg, and gravitational magnetic force, which is our Fm at a distance x, will be equal to mu1 I1 I2 divided by 2 pi x. And we assume that the current in CD is our I1 and current in AB is our I2. So both are equal. So we can write that our FG equal, rather we can say balanced FM. So we can say that our mg will be equal to mu naught I1 I2 divided by 2 pi x. And so now we come to the part B. Part 2, we say that wire AB is depressed through a small distance dx, through a small distance dx. And for the sake of simplicity, let us assume, let me rewrite this equation. I can write this as mu naught I1 I2 upon 2 pi d. Here I assume initially x is equal to d. Okay. And now the x becomes d minus dx. So therefore, separation between the wires is our x, which comes as d minus dx. Sorry, d minus dx. And this is going to cause a change in the magnetic field because the distance has been changed. You can say this will cause change in magnetic force. So we can find out the change in magnetic force with respect to distance x will be equal to, we derivate it, we get this minus mu naught I1 I2 divided by 2 pi x square. And further we can write dFm is equal to minus mu naught I1 I2 divided by 2 pi, and we know that our x is equal to d. So this comes as now d square multiplied by dx. And once again, we know that our 2 pi I1 I2 upon, sorry, not 2 pi, but mu naught I1 I2 upon 2 pi is equal to mg d. Therefore, we can write that our dFm is equal to minus mg upon d multiplied by dx. So therefore, from this equation, we can understand that the force is directly proportional to negative of dx, that is a restoring force. You can say force is proportional to minus of dx, that is restoring force, and this means simple harmonic motion. Now we can find out the acceleration. Acceleration A will be equal to change in the magnetic field divided by mass m. This gives us minus g upon d multiplied by dx. And this we can equate for an SHM. For simple harmonic motion, we have the equation that acceleration is minus omega square multiplied by x. So 1:1 comparison gives us that our omega square is equal to g upon d. And we can find out the time period now. Time period t will be equal to 2 pi 1 upon omega square. This comes as 2 pi d upon g. We simply substitute the value. We get our t is equal to 2 pi, d is our 0.01 and g is 9.8. This comes approximately as 0.2 seconds. I think this was the only thing was asked. Yeah, period of oscillation as well as executes a simple harmonic motion. So these were the questions that was asked in the year 1992, 95, 94 as well as 93. These complete the questions. Thank you.